Hey, welcome back. Today we're going to be talking about gravitational field strength, little g, for AP Physics CE Mechanics. So first I want to start with an important definition. So field is a place in three-dimensional space where if something is placed within the field with the right property, such as mass here in a gravitational field, the object experiences a force. Okay, so let's think about what we've talked about previously. We've talked about Newton's universal law of gravitation, which we have right here. And we've also talked about Newton's second law, which is a general law that applies to all forces, of course. And let's think about for a moment, what would happen if we set these two equal to each other and think about the repercussions of that. So first we would start with this m value right here, and this is m1 and m2. We need to define our m's. So if we're going to be talking about a planet and an object on the surface of the planet, then let's call one of these like the mass of an object and one of these the mass of a planet. And let's think about what we have on the left and what we have on the right. When we're talking about gravity, the force due to gravity, which we have over here, this is also called weight. By the way, notice this is not equal to mass. A lot of people confuse mass and weight in everyday speech. They're not the same thing. Weight is a force. And so if we go back over here, this would be like the mass of the object though, right? So this is the mass of the object here. One of these two, the gravitational force between like the mass of the planet and mass of the object. So we have mass of the object on both sides of the equation. Well, if that's the case, what can we do with the mass of the object? Well, we can cancel it out, right? And let's continue and see what happens. If we take a look at this, we've got our g solved for, our g isolated for, and this is not on your equation sheet, but you might want to memorize it. It's probably useful to be able to memorize this, or at very least be able to very quickly derive it like I have just done, because you're going to be pressed for time on the AP Physics CE Mechanics test, and you might want to get a list of equations to start memorizing, and this would definitely be one to add to it. Alright, so let's continue and take a look at three different problems here. So if we take a look, we're going to say the gravitational field on the surface of the Earth is basically uniform, but away from the surface of the Earth, the gravitational field strength is not uniform and not 9.81 meters per second squared. That's true. Out here, this is not 9.81, this is less. And in fact, if you look at the equation over here, it drops off quickly as an inverse squared relationship. You probably already know this concept. This already makes sense to you, most likely. You know that the gravitational field of the Earth is weaker the farther away you get from the center of the Earth. Alright, let's try three problems here. The first is just going to be a calculation problem using this equation. We do have the mass of the Earth here, the radius of the Earth here. And if you want to stop and do the calculation right now, go for it. Otherwise, I'm going to move on. Alright, so we're moving on here. Can you anticipate what would be the answer here if we threw in g, we threw in the mass of the planet, which is the planet Earth, and the radius of the Earth squared over here? What would that g value turn out to be on the surface of the Earth? Well, that, of course, is going to be 9.81 meters per second squared. So, important to realize and recognize where that comes from. So, quick recap, that comes from Newton's universal law of gravitation and Newton's second law, setting those two equations equal to each other using the mass of the Earth and the radius of the Earth. And if you do that correctly, you turn out with 9.81. I do want to point out here, this is also a really useful insight. The units for this can be thought of as being in newtons per kilogram. Alright, let's continue and do two more quick problems. So B says, what is the gravitational field going to be here at some radius that's farther above the surface of the Earth out here? Well, if we do the math, we can go ahead and say that our radius is going to be the sum of the altitude above the surface of the Earth and the radius of the Earth. Remember, Newton's universal law of gravitation applies between the center of both objects, you could say, not from the surface of the objects. Okay, let's continue. So if we plug in our numbers here, if you do the math correctly, here is going to be your answer. Just showing you how you would go about solving a calculation-based problem with numbers, with the situation of solving for gravitational acceleration some distance above the surface of the Earth. And let's do the last one. This is probably the most important, and you are almost certainly going to see something like this on your test in some format. Let's say this is planet Alpha right here, has a certain mass and radius and gravitational field strength. If we consider the gravitational field at a distance of 3r from the surface, so here's the surface, going to be 3 radii out. What is the new gravitational field compared to the surface? Okay, so this is a relative comparison problem. This is a really crucial skill that you need to develop in the course of taking an AP Physics class. So what we can do is rewrite our equation, but what we also are going to do is we're going to compare two different scenarios. We're going to compare at the surface and with an additional 3r distance away. So when you do a relative comparison, you can ignore constants because we're just going to compare the two answers. And so the constants will be the same in both cases, so they become irrelevant. And I like to use base 10, meaning for any of the numbers that we're working with, I would use like 10 for the mass of the planet and 10 for the radius. Now you could object at this point. First of all, we don't know what these numbers are. The problem doesn't give it to us. So it's appropriate to put in a number. I like 10, very easy to work with. And you could object and say, well, that's not really true. We don't know what the mass is. You're right, but you'll see how this works. It'll work out because we're doing a relative comparison problem. And if you do the math here, we get 0.1. You could also object and say this number is meaningless. Yes, by itself, it's meaningless. So let's continue though. We're going to do a comparison here. If you do that with the surface plus 3r, then you have a mass of 10 up here. Now we're going to have a radius of 40. And if you do the math here, you end up with this value. So what we're going to want to do is compare this gravitational field right here with this one, because the problem says what is the new gravitational field compared to the surface. So how would we do that? Just a quick reminder, really important reminder, these are the two relative answers we got. If we're going to compare the gravitational field strength farther away to the surface, so we're comparing this to this, that's the format of the question that we're given, then the mathematical representation of that is going to be, the first object is going to be in the numerator, and the second thing that we're comparing is going to be in the denominator. That's really, really crucial that you understand this. It's a very basic idea, but it's really crucial, and it comes up in AP Physics problems, so be careful with this. We plug in our numbers, and you can see that you have a decimal answer here. And it turns out that that's 6.25% as strong as it would be at the surface. So notice that the gravitational field strength quickly drops off the farther away you get from the center of the planet. And that's how you go about doing problems associated with gravitational fields. I will say I've done lessons on an entire year of physics, as well as most of the ideas in AP Physics C mechanics. So if you have any questions down below, please let me know, and I hope you all have a great day. Take care.